All right, welcome back, everyone. So, before we get into things, a bit of a housekeeping item for you guys. I got a new microphone, and by new microphone, I mean I found an old mic. I found the cable for my old microphone, but it's different than the microphone that you had been hearing me from. If you like the tone, let me know. If you don't like the tone, let me know. Either way, feedback is feedback, and I can make use of it. For now, we're gonna press on. So, I believe it was 2 episodes ago, we had brought up briefly the idea of conic sections. And those are things like circles, ellipses, parabolas, hyperbolas. The parabolas and hyperbolas are trajectories. We are not going to be talking about those right now. We will later, but not now. So that leaves the closed loop items, such as circles and ellipses. Circles are fairly straightforward, but ellipses are more generalized. It's kind of like how every square is a rectangle, but not every rectangle is a square. But for circles. So let's do some basic refreshing on ellipses. So an ellipse is going to have 2 foci. And for our orbital mechanics, one of them is occupied by a planet, and the other one is empty. I know I'm just going to delete it here in a second, but I want that to look like an actual triangle. I might end up deleting that part. One of them is filled with a planet. The other one is not occupied and is just empty. Now that I have spent far more time on that than I really needed to. From one focus to the short side, that is our periapsis. And from that same focus to the long side, that is our apoapsis. The two of them together are what's known as a major axis. However, over here in ellipse land, we don't care about the major axis as much as we do the semi-major axis. And as the name suggests, that is just going to be half of the major axis. Mathematically, our apoapsis and our periapsis radii, and that gets divided by 2. And that is one of those important equations to box in. As well, I think that is probably the fastest I've ever derived an equation. And I just think that's neat. So let's go ahead and figure out what the semi-major axis is for the system that we've been playing around with for the whole series so far. A equals, and if I go back over to here, conveniently, I'm already at the spots where we have our apoapsis and periapsis, 24,000 and 16,000 respectively. It's divided by 2. Which leaves us with 20,000 kilometers. Now that is a rather suspiciously round number, don't you think? It's almost as if I chose it intentionally. There are a few other properties of ellipses that we can go ahead and derive for our orbit. Some of them may be useful, some of them may not be. So we have... How about before I write down the equation, I'll tell you what it is. We have this quantity, so if this is the center line of the ellipse, going up to the widest point, that is going to be the semi-minor axis. Oh, good grief, I cannot draw. I cannot write. Let me try this again. You know what? Good enough. That is the semi-minor axis, and that is denoted as B. And geometrically, that is going to be our semi-major axis. It's just one of those days that... Oh yeah, it's one of those days. Semi-major axis times the square root of 1 minus our eccentricity squared. Managed to say that without getting tongue-tied. So for our orbit, looking at B of 20,000, square root of 1 minus 0.2 squared. That turned into 19,596 kilometers. It's a little bit less than that, but going down to the tenths of kilometers at these distances doesn't make a whole lot of sense to me. There is, off the top of my head, at least one more useful characteristic. So from one of the foci up to where it intersects with the ellipse, that's going to be slightly less than our semi-minor axis. That is going to be something called the semi-latus rectum. I have to look at my notes. I'm going to denote that as P. And what that looks like down here (1 minus E squared). All right. Once again, for our orbit, we'll just plug in the numbers. 20,000, 1 minus 0.2 squared. That will become 19,200 kilometers. Now, some of you may be thinking that this looks like a suspiciously familiar number. Well, there might be something to that. Let's go looking through the last episode. Ah, there it is. That looks an awful lot like the number that we just found. And if you're willing to forgive rounding errors, that is indeed the number that we just found. So let me... P is equal to A 1 minus E squared is equal to H squared over mu. Again, making that look more like a mu. My pen didn't want to work there for a second. Let's box that in. That is definitely something worth boxing in. All right. Well, that's pretty handy, isn't it? In fact, that might be so handy we have, instead of our specific angular momentum and our gravitational parameter, we have our semi-major axis and our eccentricity instead. Well, we looked at Periapsis, which had one of those variables here, and our Apoapsis had one of those variables here. Let's see what happens when we plug those in. So I'll do that. We'll start with the Periapsis. Root 1 plus e, bigger denominator, smaller value. All right, so we can expand that. We can cancel like terms. That'll leave us with semi-major axis minus e. That's not bad at all, is it? All right, so it's got to be, it has to be that simple for the other one, right? For our Apoapsis. Cancel. Oh, would you look at that? Indeed, it is. Indeed, it is. I'm not going to plug these into any examples. That's just going to spit out values that we already know. What I will do, though, there is one last property that I want to highlight for you guys. So if I remake an ellipse here, then I put my host body at one of the foci, and I mark the other focus. So the fun thing about ellipses is that they are symmetric. So one focus looks exactly like the other. If we have ourselves a periapsis distance over here, we know that this distance is also a periapsis, the same thing as our periapsis distance. And let's go ahead and bring it down here. This will be useful. This is going to be our, once again, our Apoapsis distance, which means that the distance between them is going to be the Apoapsis minus the periapsis. Right, you go out here like that, and then you come back in, just like that. And with the whole thing being the Apoapsis distance plus the periapsis distance, sure I use the right variable. Our eccentricity, at least in terms of geometry, is defined as the ratio of the distance between the foci divided by the major axis. Sure enough, if you were to go ahead and plug these in, if you were to go ahead and plug in these values, you would get 0.2, which is the eccentricity that we've been playing around with. That, however, will be left as an exercise for the viewer. And, you know, you've been patient with me up to this point. I've put out some fairly lengthy episodes. This one was kind of information dense, but I think I'm gonna go ahead and call it here, make it a shorter video. I'd like to thank each and every one of you for stopping by. I hope you have a great rest of your day.